We are on GLA03 page 3. The first question says use the square root property to determine all real solutions for each of the following equations. And this is actually the first question on page 3, but question 10 in the GLA3 assignment. So it says use the square root property to determine all real solutions for each of the following equations. Notice it says real solutions, so we're not interested in any solutions that have the imaginary unit in them, no complex solutions. So let's see what happens here. To use the square root property, we want to be able to take the square root at some point. So what can help is if you have anything with a square in it, if you can get that alone. So I'm going to subtract 135 from both sides first. Then I have 3a squared is equal to negative 135. Then I'm going to divide both sides by 3. And I can already tell you that this is going to be no real solutions because I've got a negative that I'm about to take the square root of. And when you take a square root of a negative, you always have I involved because I is the imaginary unit, which is the square root of negative 1. So anytime you've got a negative number, let's say you have the square root of negative 9, that could be written as the square root of negative 1 times 9, which could be written as the square root of negative 1 times the square root of 9, which could be written as I times 3 or 3I, right? So that's an example of a non-real solution or a non-real number. So we don't want that, and that's what's going to happen here because the next step when a square is isolated is take the square root of both sides to get rid of that square, get rid of the power of 2. So that simplifies to a equals, and then you've got a negative under the square root, so there's going to be an I somewhere, and then whatever the square root of the rest of it is. So there's something I that's going to be a result. So that first one, the answer is just going to be D and E. Actually says down here, give exact solutions, don't use decimals, separate multiple solutions with commas. If there are no real solutions, type D and E. So there we go. We want to type D and E because there's no real solutions here. I don't know if it needs to be capitalized. Oh, it liked it. It was fine. Okay. The other one, let's see what happens with the other equation they gave us here. So when I add, when I try to get the square term alone, and I add 324 to both sides to cancel out the negative 324 on the left. Luckily, we have a positive now on the opposite side of the equal sign, so that's good. Then we're going to divide by 3 to get k squared alone. So then we have k squared is equal to, I don't know how many, what is 324 divided by 3? Actually, I'm just going to do it right here. 324 divided by 3. 108. Okay. So we have 108 on the right. So then we take the square root of 108. Take the square root of both of these. Make sure to put a plus minus on the side opposite the variable. If you don't, you could end up with only half of the answers you should have. Right, so now we have k is equal to plus or minus square root of 108. Now, what we could say is that the solution set is negative square root 108 and positive square root 108. I'm going to separate the plus and minus into two separate answers. But I have a suspicion that 108 might have a perfect square factor in it that can be simplified. So I'm going to start thinking about all the perfect squares I know, like 1 squared is 1, perfect squares. Okay, 1 squared is 1, 2 squared is 4, 3 squared is 9, then we have 16, 25, 36, and so on. We can keep going, but just get a few of them down. Okay, so I'm up to 11 squared. I don't think it's, well, 11 squared is 121. We don't have to go that high, right? 108. So anything that divides into 108 evenly that's a perfect square would allow us to simplify this down. So what's the most likely number that might work? How about 4? I'll try 4 for a perfect square. See if it goes into 108 evenly. Okay. Does 108 when divided by 4 result in a nice clean integer? 27. Awesome. So now we have k equals plus or minus the square root of 4 times 27. And since 4 is a perfect square, I can take the square root of 4 and move it to the outside of the radical and leave the 27 in there. Now, something else about 27 is I happen to know it also has a perfect square factor. So what I did when I chose 4, I ran with it because it worked. It gave me, it divided it evenly. But if I had kept trying them, if I'd said, well, if 4 goes in evenly, I wonder if another perfect square that has that 4 divides evenly might work. And what I would have discovered is that 36 also divides 108 evenly. 108 divided by 36 will give me 3, right? So that's another path I could have taken, is I could have said k is equal to plus minus square root 36 times 3, and then the square root of 36 is 6, so I could have written it like that, okay? However, I didn't do that. I didn't use 36. I first used 4, and I ended up here, but it's not too late to get to the right answer. Now that I realize that 9 divides evenly into 27, right? Because 27 divided by 9, which is a perfect square, 9 is a perfect square, gives me 3. So then I end up with, what I have so far is 2 times the square root of 9 times 27. Oh, no, sorry. I don't want to confuse you. 3 times 9. That's what I meant to say. The square root of 9 can come out of the radical. So I have k equals plus minus 2 times, now it's the square root of 9. What's the square root of 9? It's 3. So that comes out of the radical, and the other 3, the 3 stays in there. The 3, I leave this 3 right here. We'll do a little color coding. This 3 right here is still stuck under here, under the radical. Okay. Now the 2 times 3 becomes 6, and I end up at the same answer from over here. Okay, so noticing that 36 divides evenly into 108 would have been the quickest path to the correct answer, but not the only path to the correct answer. So what did we learn from this? We learned that you should list out all your perfect squares and start dividing them into your radicand. And if you find one that works, go a step further and see if there's a bigger one that works, because that'll make it easier for you. But if sometimes you don't realize it, you might, after you've gotten one thing simplified, you might realize that you can continue to simplify, and that's fine, and you can still end up at the right answer. So we would write these separately. We would write it as negative 6 times the square root of, what was it, 3, comma. But also remember, anytime you're in a fraction or under a radical, something like that, and you want to do your comma, you're going to need to get outside of that square root. For instance, in this case, I'm going to use my right arrow key. And now I'm outside of the square root. So when I put my comma, it's not stuck underneath the radical. Because you need to notice when I was still under there and I put the comma, you see I'm getting a warning about syntax, because that comma is not supposed to be under there. It's supposed to be on the outside of the radical. And then 6 square root 3. Good. Okay, next question. Solve for x using the square root property. Okay. This one looks a little more complex, but I don't think it's too much worse. We're still going to try to get everything except the squared, everything except a perfect square involving x on the left. So we'll go ahead and write this on the other side hold on, hang on. Okay, so like I said, let's go ahead and remove anything from the left side except for a perfect square. We're just going to keep going until we have a perfect square all alone on the left side of the equals. All right, now we have added 69 to both sides so that the left side is just 3 times x squared now. And then when you add negative 54 plus 69, or when you subtract 69 minus 54, you get, what is that, 15? Okay. Now we're going to continue to isolate that perfect square. So I'm going to divide by 3 on both sides. 3 divided by 3 is 1. 1 times x squared is just x squared. And now we have x squared is equal to 15 divided by 3 is 5. Now we are in a situation where we have a perfect square involving only x on the left. Well, it doesn't have to always be only x. It can be a quantity squared that has x in it. But whatever's there has to have the power of 2 on the outside of it. We didn't want the 69 over there, the negative 69 over there, because it was not being squared. And 69 is not a perfect square. And it's separated by a minus, which makes these two separate terms. We just want one term that is a perfect square. Okay, it could be a quantity of several terms, quantity squared, but anything just off on its own that's not being squared, that's going to be a problem. So now we have a perfect square expression on the left and 5 on the right. So we're going to take the square root of both sides, remembering to always put a plus minus on the side opposite the variable. And then we have x equals, you could say negative square root 5 or positive square root 5. Okay, now you might be wondering, I haven't mentioned why. I try not to do that in these videos. I'm just showing you how to solve it. But you might be wondering why the plus minus has to be there. Because if, let me explain an example with a real number. So 2, let me get something else. So let's do 3 squared. That gives you 9. But also negative 3 quantity squared, which is negative 3 times negative 3. And when you multiply two negatives together, you get a positive, also equals positive 9. So if I were to say, hey, there's this certain number that when squared gives you 9, tell me what is x, what number, what value of x could go here and make this a true statement. To say that x is 3 is not complete because x could also have been negative 3, right? So that's why we always need the plus minus so that we can have both of those options in our solution set. All right, and so that is the end of this. Whoopsie, forgot to get outside my radical again before putting the comma. Get outside the radical, then put the comma. All right, now that's the end of this page, so I will see you in the next video.